In this section, we consider in more detail the energy involved in fission when uranium-235 captures a neutron to form the compound state uranium-236 star. The star is represented the new compound state. Then calculate the excitation energy using the following equation. The energy of the compound state can be found directly from the mass energies of uranium-235 and neutron. If we assume the neutron's kinetic energy is so small that it is negligible, then the mass of uranium-236 star equal to mass of uranium-235 plus mass of neutron. Then we got the total mass. After calculating the mass, then the excitation energy is given by 6.5. The activation energy for uranium-236 is calculated also to be 6.2 MeV. Thus, the energy needed to excite uranium-236 into a fissionable state, that is exceeded by the energy. By adding a neutron to uranium-235, this means that uranium-235 can be fissioned with zero energy neutrons consist with its large observed fission cross-section in the thermal region. A similar calculation for uranium-238 plus neutron gives uranium-239 gives the excitation energy correspond to this 4.8, which is 4 smaller than the calculated activation energy of uranium-239. 6.6 MeV neutrons of at least MeV energy are therefore required for fission of uranium-238, which is consist with the observed threshold for neutron-induced fission of uranium-238. The primary explanation for the extreme difference in fissionability of uranium-235 and 238 thus lie in the difference between their excitation energies, respectively 6.5 and 4.8. This is the corresponding activation energy graph. The excitation is therefore reduced by delta related to its value without the pairing force term. The difference in excitation energy between uranium-235 plus neutron and uranium-238 plus neutron is therefore about 2 delta or 1.1 MeV, which nicely account for most of the observed difference. The neutron captured by any odd n nucleus will lead to the more stable even n configuration, with a corresponding increase in excitation by delta. Captured by even n nucleus will lead to reductions in excitation energy by the same amount. We consider the energy released in fission and the specific set of final products the following equation. The Coulomb repulsion will drive the two fragments apart, converting the potential energy into kinetic energy and giving them of order 200 MeV of kinetic energy in the process. There are two highly probable energies about 66 and 68. These correspond to the heavy and light fragment respectively. M1v1 equal to M2v2, from which it is easy to that the ratio between the kinetic energy should be inverse of ratio of masses. Give the following equation. The ratio 66 MeV by 98 MeV equal to 0.67 is entirely consistent with the ratio of most probable masses obtained from the figure. The distribution of energies thus appears to be characteristics of the distribution of masses and suggests that on average 165 or roughly 80% of fission energy appears of kinetic energy fragments. This is the corresponding representation of pairing on excitation energies. The figure shows the distributions of prompt neutron energies following fission of uranium-235. The mean energy is about 2 MeV and with an average of about 2.5 neutrons per fission, the average energy carried by the neutrons in fission is about 5 MeV. This also suggests that the average neutron carries a momentum only 2% that of either of the fragments, thus neglect the neutron momentum and other energies released in fission appears as follows. Then beta decays from radioactive fragments 19 MeV, gamma decays from radioactive fragments 7 MeV. These are only estimate and will obviously depend on the exact nature of fragments and their decay within 1 to 2 mega electron volt. They are characteristics of most decays. The prompt gamma is emitted essentially at the instant of fission. The beta and gamma radiations are emitted according to the decay schemes of chain of heavy and light fission fragments. The beta energy is on the average about 30 to 40% given to beta particles with the remainder going to neutrons. The neutron energy is lost and contributes neither the energy recovery of heating of reactor fuel nor to the dangers posed by the radioactive waste products. This have a graphical representation. This is the corresponding representation of this.